Swayam Prabha. Digital India. Educated India.
Welcome back. So, in the last lecture we just talked about the construction of flow nets with the help of equipotential lines and flow lines, and I hope, and this is the basic and this is the backbone to understand the seepage analysis. So, if you understand this thing properly, then it is it will be very clear to you that how we can find out the flow through the porous medium. So, in the flow net construction, basically with the help of equipotential lines and flow lines, you will be constructing some grid or the net kind of thing, which you will be solving for different information. And there we have seen how you will be getting different flow channels through which the flow actually will be occurring, and flow channels will be bounded by two successive say flow lines. And whereas we have got equipotential drops, that is ND, that is happening between two successive say equipotential lines. So, these few things we have seen in the last lecture. Now, in this lecture we will be seeing more information about the flow nets. So, drawing a flow net takes several trials, as you have understood from this that see number of flow lines and number of equipotential lines are solely dependent on your own judgment, right. So, you can go for say 6 number of flow lines or 8 number of flow lines or maybe 50 number of flow lines, right. So, it is based on your judgment and it should satisfy two basic criteria. One thing is flow lines and equipotential lines, they intersect in 90 degree and that will form 90 degree angle at the intersection point, and the flow lines and equipotential lines will be or the flow domain or the region will be constructed, the element, right, flow element should be all approximately equal to a square. So, these two criteria you need to satisfy when you are forming the flow lines or when you are constructing the flow nets rather. So, basically, so it will take several trials. So, suppose you are starting with say 6 number of flow lines and 8 number of equipotential lines, say suppose for any kind of problem, and if you see that they are not satisfying this thing properly, then or maybe they are satisfying this thing, but you can have better opportunity to improve the result by increasing the number of flow lines and number of equipotential lines. So, as you increase the number of flow lines and equipotential lines in the flow net, your results or your values whatever you are expecting or whatever you are desiring to obtain from this flow net, so those will be refined further. So, this is the kind of say optimization kind of thing, and further if you increase the flow lines and equipotential lines, and at certain point of time you will see that you are not getting any refinement in the results. So, that means you are getting the maximum efficient say flow nets, right. So, this will take several trials. So, you can nobody can say that okay, this flow net if you use you will be getting the right answer, right. So, that depends on individual to individual perception and how you are proceeding by doing, I mean systematically you have to proceed by analyzing that thing through sensitivity analysis and get the results. So, for the flow net shown, whatever we have seen in the last lecture, the following 4 boundary conditions apply, right. The upstream and downstream surfaces. So, if I see the flow net once again, whatever we have seen in the last lecture. So, let us go back. So, this was the flow net we have seen in the last lecture, right, or there we have seen. So, the thick black lines are nothing but the flow lines, whereas the dashed line is are nothing but the equipotential lines, and we have seen how they are forming the flow channels and equipotential drops ND. So, now if you see here, so we have defined several say lines AB, D and GF and AC, DC, all those things, right. So, we will define all those things properly now. So, now basically what are the different boundary conditions are applied in this particular flow net? the upstream and downstream surfaces of the permeable layers, okay, AB and DE are equipotential lines. Do you agree with that or not? Because already we have seen that this line is equipotential line AB, that means on the upstream side the bed, okay, and on the downstream side the bed, that is DE, are the equipotential lines, right. So, this is the first boundary condition. Now, second one is, because of AB and DE are equipotential lines, all the flow lines intersect them at right angles, it has to be, right. So, that is the important criteria for flow lines and equipotential lines to be constructed. So, the boundary of impervious layer. So, if I am putting the figure once again. So, if the boundary of the impervious layer, that is Fg. So, this is your boundary of the impervious layer, Fg is a flow line, right. Do you agree? Because you are considering the flow lines, the flow can occur along this line. So, is the surface of the impervious sheet pile ACD. So, this line is also a flow line. So, flow can occur, flow cannot occur across the sheet pile, but it can occur along the line, along that line ACD. So, it is one of the flow lines. Now, the equipotential line intersect AD, ACD and FG at right angles. So, equipotential line, whatever equipotential line is cutting or intersecting the line ACD as well as FG, they will be making 90 degree. As you can see, they must be 90 degree. So, this is also 90 degree, this is also 90 degree and so on, this is also 90 degree. So, these are the things must be satisfied, then only you can say, okay, this is my right flow net I have constructed. Okay. In a flow net, the strip between any two adjacent flow lines is called a flow channel, right, already we have seen. So, try to understand the strip, that means the region between any two adjacent flow lines is called a flow channel, and through which actually the flow will be happening. I mean, if you try to remember, I will try to map this thing by mapping it with some pipe flow or something like that. Through the pipe, actually within the inside or inner diameter, the flow will be occurring, right. So, this is something like flow channel. So, it is bounded by two flow lines, which will be eventually, which you want to map with the pipe flow. So, that will be nothing but your pipe surface. Okay. So, now if you look at, so this is very typical say flow channel with square elements. Now, you can see, so this is one flow line, this is another flow line. So, adjacent two flow lines are basically forming the flow channel. The flow is happening in this direction. So, delta q is the rate of flow or the flow amount or the flow quantity discharge. So, basically that is happening through this flow channel. Now, you are getting different equipotential lines like this, like this, like this. So, these are all equipotential lines. Okay. So, now from this, say from equipotential line 1, if you come to equipotential line 2, you are getting the head drop. So, it was H1 along equipotential line 1, now it is H2 along equipotential line 2 and so on, right. And the elements, okay, the elements bounded by this flow line, equipotential line, another flow line and equipotential line, this is nothing but square. So, that is another requirement for constructing the flow net. So, that dimension is given by L1 by L1. Similarly, L2 by L2, that is forming another square, that is also another element. Similarly, L3 by L3. Now, the flow is happening say within zone 1 or the element 1. So, this I say element 1. Okay. Within element 1, the flow is happening say delta q1, within element 2 flow is happening delta q2 and delta q3 and so on. Now, if you want to satisfy the continuity condition, so delta q1 must be equal to delta q2 must be equal to delta q3, there is no other way out, because flow is not happening or water is completely incompressible. So, there is no change in volume. So, whatever water is getting inside the flow channel, the same amount of water will be going out from the flow channel. So, now this the last figure or the figure 32 shows a flow channel with equipotential line forming square elements. So, last figure we have seen. Let small h1, h2 up to hn be the piezometric levels corresponding to the equipotential lines, already we have seen in the last figure whatever we have seen. Now, because there is no flow across the flow lines, because it is not allowed at all, because when you are drawing the flow lines and when you are constructing some flow channels, basically flow cannot occur across the flow lines. So, it cannot cross the beside whatever flow lines are there, it cannot cross those flow lines, it will flow along the flow channels only, right, it is allowed. So, delta q, as I told you, delta q must be equal to delta q1. What is delta q1? That is the discharge of the flow happening through element 1, okay, must be equal to delta q2 must be equal to delta qn if you have n number of elements in the flow channel. So, as per Darcy's law, we can write delta q is nothing but k into, if I say the k is same, okay, so kx as well as kz both are equal, that is isotropic soil, and for that say k is the coefficient of permeability. So, if that is true, then delta q is given by k I into cross sectional area. Now, what is I? I is nothing but from, say, for element 1, if I consider for element 1, what is the hydraulic gradient? I is nothing but h1 minus h2, that is the head drop happening from equipotential line 1 to equipotential line 2, if you recall the figure whatever we have seen just now. So, k into h1 minus h2 by what is the length of the element, that is L1 into area, area is L1 into unit length normal to the screen or normal to the board, right. So, L1 into 1 is nothing but the cross sectional area through which the flow is occurring. Similarly, so this is giving me the flow, that is the delta q1 through the element 1, this is the flow happening through element 2, that is k into h2 minus h3, that is the head difference happening from equipotential line 2 and equipotential line 3, and L2 is nothing but the length of element 2 and cross sectional area of element 2 is L2 into 1, right. So, if the flow elements are square, the drop in piezometric level between any two adjacent is the same, am I right or not? Please try to understand. If the flow elements are square, okay, the drop in piezometric level between any two adjacent is the same, which is called the piezometric drop, right. So, h1 minus h2, because if you satisfy this equation, right. So, in this equation basically h1 minus h2 must be equal to h2 minus h3, must be equal to h3 minus h4 and so on. So, I am writing that thing here. So, h1 minus h2 must be equal to h2 minus h3 and so on. So, which is eventually capital H, that is the total head difference, okay, between the upstream and downstream side divided by the number of potential drops. That means, how many number of potential drops you are having. So, in the flow net construction we have seen how many number of potential drops are there, 6 number of potential drops you had or you exhausted starting from the upstream side to the downstream side. So, that means, the total head difference between upstream and downstream side divided by the number of potential drops will give you the difference in each element head or head difference at each element. So, if the number of flow channels in a flow net is equal to NF, whatever we have seen in the flow net construction, that how many flow channels you are constructing, the total rate of flow through all channels per unit length can be given by total Q, that is the discharge happening through the porous medium or the pervious or the permeable medium, is nothing but K that into H by ND, that is nothing but your that is nothing but your whatever potential drops you have seen in the last slide, right, H1 minus H2, right, into NF. NF is the, so K into basically if you come back here. So, delta Q is nothing but right, delta Q is equal to K into H by ND, right, from this, from whatever we have seen just now from equation 2.15 and 2.16, we can see that delta q is equal to k into h by n d. Now, this delta q is happening through n number of say flow channels. Now, total flow is nothing but k into h by n d into n f, that is the number of flow channel, right. So, that is the total flow. So, if you are asked to find out the total flow happening through some permeable medium, so you first construct the flow net and then you find out n f and n d, and then of course, h is known to you, that is the head difference between the upstream and downstream side, and if you know the coefficient of permeability or the hydraulic gradient of that particular soil, you can find out total discharge or flow, that is q. Alternatively, rectangular meshes for flow channel can be drawn, because already we have seen whatever we have seen so far, that is basically based on some square element. So, you are only allowing square element within the flow channel. Now, you may have or you may construct the flow net in such a way that your elements are coming as rectangular, right. So, rectangular meshes for flow channel can be drawn, provided that the width to length ratio for all rectangular elements are the same. Okay. So, that means, if I construct the flow channel with rectangular elements, now you see this is your first equipotential lines, this is your second equipotential lines, this is your say flow line 1, flow line 2, and this is the element you have which is rectangular, where L1 is the length, B1 is the width. Okay. Similarly, this is your element 2, which is another rectangular element, this is element 1, this is element 3, which is another rectangular element. Now, if this is happening, or if you are constructing the flow net with this kind of rectangular elements, so you must remember that this ratio should be maintained, that is B1 by L1 must be equal to B2 by L2 must be equal to B3 by L3, say some ratio n. So, at least you need to do this thing if you are considering rectangular elements. Okay. Now, if you consider rectangular elements, then basically your delta q will be equal to delta q1 equal to delta q2 equal to delta q3 and say up to delta qn. So, your delta q1 is given by k into this is the I, that means the hydraulic gradient within element 1, that is H1 minus H2, that is the head difference between two successive equipotential lines, divided by L1, that is the length of the element, rectangular element, into area, that is B1 into 1, right. So, that will give you Q1, delta Q1. Similarly, delta Q2 can be obtained like that. So, we can write down delta Q is equal to K into H1 minus H2 into N equal to K into H2 minus H3 into N and so on. So, the discharge is delta Q is equal to K into H into N d. So, H by N d is nothing but your difference, that is H1 minus H2 into this N. So, whatever, if you remember from the square element, basically we had got for square element that K into H by N d. So, for square. Now, for rectangular element, basically you are getting K into H by N d into N, right, because this N is coming into the picture. So, total discharge will be then multiplied by the flow channel, number of flow channel, that is N f. Okay. So, that will give you the total discharge happening in the permeable medium if you consider the rectangular elements in the flow channel. So, now if n is becoming 1, you are getting the same solution whatever you have got for the square elements. So, this is basically more general, and you can have square elements as well as rectangular elements, there is no issue, but equipotential lines must intersect the flow line perpendicular normally or the orthogonally. Okay. So, we have seen the total flow if you consider the rectangular element as well as if you consider the square element. So, only difference is that small n, that is the ratio of your or the aspect ratio basically for the element is coming into the picture. So, we will continue in the next lecture. So, today we will stop here, and we will see in the next lecture that how you can find out other information from the flow net and other details. Okay. Thank you very much.